Hello, in this video we're going to continue our tour of Chapter 10, where we talk a little bit about the various types of chemical reactions, and then in this video we'll really focus on the double replacement precipitation type reactions. Okay, so there's a number of different ways to classify chemical reactions. The stereotypical Gen Chem version is listed here. You can have a combination reaction where two things will come together and form a product. You can have a decomposition reaction where one product will dissociate into two different pieces. You can have a single replacement reaction where you have some ionic compound, Bc, and then say the cation changes with a free cation, and this is often called displacement. Then you can have a double replacement reaction where you have a cation and an anion, say AB. You have a different cation and anion, CD, and then they trade cations and anions to form new products. I'm not, admittedly, a huge fan of this classification system. I think it is a little pedantic and minimizes the beauty of chemistry into, four simple rules of reactions, and I don't really like it. I wanted to include it here because somehow I feel remiss if I teach you a chemistry course and don't tell you what a single replacement reaction is, but I wouldn't be too concerned about this. And so therefore we'll skip sections 10.7 and 10.8. Okay, this one we're going to cover though, because I think this is important chemical insight that I want to introduce you to here. So these are called double replacement reactions, and another good way to call them is a precipitation reaction. And so these result in the formation of an insoluble product, which we call a precipitate. So if you're not part of the solution, you're part of the precipitate. So what happens, and this will be our example we'll use to describe this, what happens if you combine nickel chloride, aqueous, and sodium hydroxide, aqueous? Now before we plunge headlong into this, I want to remind you that there's a couple different ways you can write this. So the simple way to write it, the molecular way, is you write it as if nickel chloride is a molecule, so you stick the formulas together, and then sodium hydroxide is a molecule, you stick that together. This is a really common way to write it just because it's simple and it matches our conception of what's in the bottle, maybe our misconception of what's in the bottle. Now in reality, if you have nickel chloride and it's soluble in water, it will dissociate into nickel 2+ and then two chloride anions. And this is something we talked about in chapter 6 of the behavior of ionic compounds that are soluble in water. They're electrolytes and they dissociate into positive and negative ions. Similarly, the sodium dissociates into sodium plus and hydroxide, OH-. So the listing on the bottom here is the more fundamentally physically correct way to describe what's going on here. You have a bottle labeled nickel chloride, it contains this stuff, and you're going to add it to a bottle named sodium hydroxide, which contains dissociated sodium and hydroxide ions. So you'll see us interchange between these two ways to write formulas. The top one's a lot easier to write, so we tend to do that. However, the bottom one is the more fundamentally correct one, so we'll do that at times too. It just depends on what you're trying to show with the language of the chemistry. Okay, and now we're back to our original question. What happens when you combine nickel chloride and sodium hydroxide? So, if any two of these ions can combine to make an insoluble product, then you'll get precipitation. So for instance, if the positive nickel and the negative hydroxide ion combine and they form something that's insoluble, then you'll make a precipitate. Or if the chlorine and the sodium come together to form something insoluble, then that will precipitate. Sometimes you get both to precipitate, although that's kind of rare. Usually one of these pairs will precipitate, and then you'll make the reaction happen. Or, quite commonly, you mix these together and nothing happens, and then you don't get a reaction. You just now have a mixture of four different ions dissociated in the same bottle. So how do we go about predicting these things? Well, the process here is pretty simple. So first you write down the reactants, and then they trade partners. So in the products section, after the arrow, you'll trade the anion and the cation with each other. So you can imagine it like a weird double date. They come together in one pair and then they go home with the other one, right? And so when putting these together, you have to be cognizant of charges of ions to figure out the formulas, right? So if you look down on the bottom of the screen, it's nickel parentheses hydroxide 2, because nickel is 2 plus and hydroxide is 1 minus. And we know that nickel is 2 plus because it's over here hanging out with 2 chlorines. Each chlorine's a -1, so that means this has to be a +2. So when you're putting these formulas together, you have to keep that in mind. Sodium and chloride go together in a 1-to-1 ratio, things like that. Then, check to see if any of the products that you made, so here are your 2 potential products over here, check to see if any of those are insoluble. If they're insoluble, then you write an S after the product in its physical state for either product. And if it's not, then you just say no reaction. So instead of writing products, you would just say no reaction. So this leads us to a big question. How do we know what's soluble? We need to have a way to figure that out. And for that, we use what's called a solubility table. So here's the solubility table from your book. And it's set up like a series of rules where the rule on the top supersedes the rules on the bottom. So just some examples of how this might work. Say you have silver chloride. Silver is on our list of ions that only take 1 charge. It's +1, so silver chloride looks like this. So as we're going down the list, let's see here. Alkali metal, ammonium, nope, not us. Nitrates, acetates, perchlorates, nope. Here we go. Most silver salts are insoluble. So this is the one that's higher on the list, so that means that this is not going to dissolve in water. Even though number 4 on this list tells us that most chlorides are soluble, the fact that this is paired with a silver ion and that silver's higher on the list means that overall this thing is insoluble, irrespective of whether this is a chloride ion right here. So again, it's a list of priority orders that tell us whether something's soluble or not. And most of this list was determined experimentally and arranged into a format that makes it hopefully easier to use. Alright, so back to our question here. We have our nickel chloride and we have sodium hydroxide. Well, again, as a demonstration of how the solubility rules works, nickel and chloride is rule number 4. Most chlorides are soluble, and nickel's not on this list specifically, so that means we're going to go with whatever the rule is for the other anion, in this case the chlorine. So it's soluble based on rule number 4. Sodium hydroxide is soluble based on rule number 1. Great. So now what about our products? So the nickel hydroxide, well, most hydroxides are insoluble, and nickel's not listed anywhere in the solubility rules, so that means that this is a solid. Now remember, before, sodium hydroxide was soluble because the rule number 1 for most alkali metals, of which sodium is an alkali metal, rule number 1 overruled rule number 5 below it, because it's higher in the list. But after the double displacement reaction, now we have nickel hydroxide, which there's no other rule to save it, so this thing turns out to be insoluble. Then sodium chloride, that's table salt. Most alkali metal salts, the sodium, are soluble, so this is still aqueous. So looking at this reaction, this forms a precipitate. You get the nickel hydroxide precipitate. It's a solid that will fall out of solution upon mixing nickel chloride with sodium hydroxide. Okay, so that leads us to the question of how do you define solubility? And so you have to draw a line somewhere, even though solubility varies on a spectrum from crazy insoluble to very soluble. And so the arbitrary line we draw is that something is soluble if more than, say, 10 grams per liter will dissolve in water. Something slightly soluble if, between 10 and 0.1 grams per liter will dissolve in water. And then something insoluble still is a little soluble, but it's less than 1/10 of a gram in a liter of water. And so the solubility rules table here only lists what's soluble. It doesn't include the slightly soluble. And we're not going to get down the road of having you do problems with slightly soluble ions and try to figure out what happens. That's not what we're going to do here. We're just going to stick to soluble or insoluble. Now, I'm sure the question you are asking is, what do you need to know for the test? And I want you to know some of these solubility rules up to 5, knowing that hydroxides are insoluble. So just the part that's unshaded here is what you have to know for the test. And again, my reason here is I want you to become functioning scientists, and some insight just generally about what is soluble and what is not, I think is very helpful for being able to move forward as a scientist and quickly solve problems. So I do want you to learn some of these. If you only learn a little bit of it, at least know that the alkali metal salts are soluble, and then you can get pretty close with the rest of it. But do try to know all of the stuff that's not shaded, and that's going to help you out on the test. Okay, so now another thing we can do is talk about molecular and ionic equations. So I already mentioned this briefly, that molecular equations you write as though all species exist as molecules or whole units. And we know that's not exactly true, it's just that it's a heck of a lot easier to write it this way. So this is what we saw before. The nickel hydroxide, nickel 2 hydroxide is a solid, and then sodium chloride is aqueous. Perfect. Now, ionic equations, or sometimes this is called a total ionic equation, this will show all of the species that are soluble dissociated as their free ions. And keep in mind, if you have 2 sodium hydroxide, it means you make 2 sodium and 2 hydroxide. Now, when you're writing the ionic equation, the nickel hydroxide is a solid, and solids that don't dissolve in water, they do not dissociate into their constituent ions. And so therefore, nickel hydroxide as a solid, you leave it stuck together in the ionic equation because it doesn't actually dissociate. It's stuck together as a solid. It's not so present in solution to interact with your other components there. But the sodium chloride is soluble in water, and so that we leave dissociated as free ions. Now, if you notice, the sodium and the chloride ions don't change on either side of this equation. And so we call these spectator ions. They're not involved in the reaction, they're just sitting on the side and spectating, watching what's going on. And while they're the same on both sides, you could cancel them out and still describe pretty much the same chemistry. So this is something that we do often. We'll write a net ionic equation where only the species that are actually taking part in the reaction are represented. So the nickel 2 plus, the 2 hydroxide anions, they make nickel hydroxide solid. This is the part that's changing left to right in this reaction. And so this is the part that we want to include when we're talking about the net ionic equation. Remember, net means summed up. So the sum, the overall outcome of this is, here you go. Now we can use these ideas of molecular ionic and net ionic equations to fully describe a reaction. For example, here we have calcium chloride and sodium carbonate. What happens when you mix these two together? So the first thing we do is write the molecular equation. Now, okay, here's calcium chloride. Calcium's 2 plus, the chlorine is minus 1, so there's 2 chlorines for each calcium. And then sodium is a 1 plus. Carbonate is a 2 minus, so they come together like sodium 2 carbonate. Now, each of these are aqueous, and you can look at the solubility rules and prove to yourself why that would be. And then we're going to make products. So we take the calcium and the carbonate, and we mix those together, put those together, I should say. We take the sodium and the chloride and put those together. So what do we get for physical states? Well, if we look up in the solubility rules for the calcium carbonate, carbonates are insoluble, so that means the calcium carbonate is a solid. Notice that calcium and the alkaline earth metals, to which calcium belongs, are not present in the solubility rules at all. So we can't use that to decide. We have to look at the carbonate. All right, the next thing is the sodium chloride. Well, rule number 1 says that all alkali metal salts are soluble, so that means the sodium chloride is soluble. So this is our molecular equation. So let me rewrite that here. Perfect. So now let's look at the ionic, sometimes called the total ionic equation, just to emphasize that you're splitting out all of the ions. So calcium chloride is soluble, so you take calcium 2 plus, and then you take 2 chloride anions, because within the formula unit for calcium chloride, you have 2 chloride ions. So you have to write a 2 coefficient in front of that. And you really need the physical states, the parentheses AQ for aqueous, which means dissolved in water. So you need that here also. Then the sodium carbonate is also soluble. So you put a 2 in front of the sodium because there's 2 of them in the formula when it dissociates. And then you have the carbonate there, which is a -2 ion. And both of these are aqueous because they're dissolved in water. Okay, so then we go to make products. The calcium carbonate is a solid, so you keep it together in the ionic equation. Because it does not dissociate into its constituent ions, we do not show it split apart like that. So there's calcium carbonate. And then the sodium chloride, on the other hand, is still soluble. And since there's a stoichiometric coefficient 2 in front of the sodium chloride in the molecular formula, we need to keep that 2 in front of the sodium ions and the chloride ions in the ionic formula here. So this is the ionic or total ionic equation for this reaction. And this is illustrative of what's actually happening when you combine these two together. Now we often want to talk about net ionic equations because this is the effect of what's happening. The calcium and the carbonate come together to make calcium carbonate. So I kind of lightly scratched out the spectator ions that are the same on both sides of this equation. So then you put together everything that's not a spectator ion into the net ionic equation, and it looks a little something like this. Perfect. So now we've finished this example. We wrote the molecular, the ionic, and the net ionic equations for the precipitation reaction of calcium chloride and sodium carbonate. So that's all we have for this video. Thanks for watching.